So today we're going to look at what are the various factors that can affect how a lens acts. So first of all, you may have noticed that we've been focusing on double convex lenses and double concave lenses, but if you take a look at your glasses, they are both convex on one side and concave on the other. So the way you can tell how it acts is which side dominates. In other words, if we have an end that's concave and convex, if it's more convex, then it's going to act like a converging type lens. And if it's more concave, then it's going to act like a diverging type lens. And actually, let me draw these a little bit more extreme. So, for example, if you have a lens that looks like this, a little bit concave, and then extremely convex, that's going to be a converging type. If you have one that is extremely concave and then a little bit convex, this is going to be a diverging type. So why don't you take a moment right now and look at your glasses and see what kind of lens that you have. Do you wear diverging lenses or converging lenses? So next, I have a series of questions that I'd like to ask you, and I'd like you to take a moment to answer these. Push pause and answer these before moving on. So what I want to know specifically is how will the focal length change if, number one, the lens is thicker, number two, the index of the refraction is larger, number three, if you take your lens and you place it in water, number four, if you take your lens and now place it in a medium with a greater index than the glass itself. And number five, the size of the lens increases. So not the thickness, but the size. So again, push pause, try to answer these questions. And honestly, this is probably one of the most important skills of this unit. Can you take a concept that you've learned in the past and apply it into a unique situation? So try to answer it for each of these and think through the logic, and then I'll go over it with you. So the first question is, how will the focal length change if the lens is thicker? Let me go ahead and draw this out for you. So here we have our two lenses. We have our thin lens and our thick lens. So let's imagine light's coming in to our thin lens. Okay, it's going to refract on one surface, refract on the second surface, and keep going. Take another parallel beam, it's going to refract and refract. Here's our focal length right here. So on our thick lens, notice what's going to happen. On that first refraction, since it has more space to bend, it will continue to bend inside the lens. And on the second, at the bottom, same thing. It's going to have more time, more room to bend. And what you're going to get is a focal length that is closer here to the lens. Okay, so again, when we take a look, we have more curvature, means we're going to have more refraction overall. If there's more refraction, we're going to end up with a shorter focal length. So let's look at the second question. How will the focal length change if the index of refraction of the lens changes? So let's go ahead and draw this out again. All right, so here we have our two lenses. And so the first one, we're just going to treat this as just kind of a normal situation. It's going to bend, it's going to refract, and we're going to get our focal length over here. Now in this one, since the index is larger, that means that there's going to be, because of Snell's law, there's going to bend more, the light's going to bend more. And so at the two interfaces, we're going to get more bending, and because there's more bending, we're going to end up with a shorter focal length. So our conclusion is if the index of refraction increases, you're going to have, if you have a higher index, there's going to be more refraction. You end up with a shorter focal length. Question number 3, how will the focal length change if we take our glass lens and place it into water? So here's this situation. We're going to take our lens, normal glass lens, and the normal situation would just be in air. So it's going to look like this, like this, like this, and same thing. Refract, refract. There's our focal length. Okay. Now we're going to place it in water. So remember, the index of refraction is not just the amount that it refracts is not just dependent on the index of refraction, it's the difference between the two. So from here we're going from 1.5 to 1. Here you're going 1.5 to 1.3. So the difference is less. Since there's less difference, there's going to be less refraction. And so when this one comes through, it's not going to refract very much. This one goes through, it's not going to refract very much. And so what you're going to end up with is a longer focal length in this case. This situation actually you've probably experienced if you ever looked underwater and notice that things appear blurry. That's because if this is the lens of your eye, normally your eye expects to go from air to your eye, right? Well, when you're underwater, it's going from water to your eye, and so your index of refraction is actually changed. How do you remedy this? Well, you wear goggles. When you wear goggles, now you have this little space of air in between your eye and the water, and so now it acts like a normal situation and things are going to get clear. Okay, so the answer to this question, if you put the glass in water, there's going to be less refraction and therefore a longer focal length. All right, well, how will it change if we now place an index larger than glass? All right, so here's our normal situation. Over here we have just kind of our normal refraction. So notice here we're now going to go from 2.4, this is on the outside, to 1.5. So recall here when we go from small to large, it bends towards the normal. However, in this case we're going large to small. So instead of bending towards the normal, it's going to bend away from the normal. And likewise over here, it's going to bend up and away. So notice in this situation, when you reverse the indices of refraction, you're actually going to change this from a converging type lens into a diverging type lens. So again, what's going to happen is when the refraction is going to be opposite, and therefore it's going to act like an opposite lens. So a normally converging lens will actually now become a diverging lens. The same would be true if you took a diverging lens and flipped it as well. It would now act as a converging type lens. So the last question was, how will the focal length change if we change the diameter or size of the lens? So in this situation, everything's going to be the same. The curvature is going to be the same. The index of refraction inside and out is going to be the same. The only difference is the diameter, the size of this. So notice when we draw this out, since everything's the same, the amount of refraction will also be the same. And so for this one, you'll get a focal length something like this. This one, you'll get a focal length, something like this. I'm not going to draw this perfect, but I'll do my best. So anyway, the point is that the focal lengths will be exactly the same. Now the only difference is, since there's more room here, there's more light that's going to be collected. And so, if we kept drawing more beams, and they're all going to intersect, since you have more light being collected, ultimately, the image itself, like when you draw out the image, it would be much brighter because there's going to be more light. But the focal length itself would stay exactly the same. All right, so the conclusion again is if we increase the diameter of our lens, it's going to have no effect on the focal length. The only thing it will affect will be the brightness. So let's see a few of these concepts in action. Here's an example of a lens we have here. What I want you to do is watch the focal length. What's going to happen is I change things. You can also watch the image as well, but mainly take a look at the focal length. So if I make the image thinner, if I make the, fatter, if I make the lens fatter, notice the focal length comes in. If I make the thinner, we're going to push the focal length back farther. Okay, how about the refractive index? This is a 1.5 index of refraction of the lens. If I decrease the index of refraction, notice that the focal length gets pushed away. If I increase the index of refraction, we're going to get more bending and it's going to come inward. Lastly, let's look at the diameter of the lens itself. So this one, if I make this lens larger, Notice that there's no effect on the focal length at all. If I make it smaller, there's no effect. I don't know if you can tell in the video, but the brightness of this does change. That's the only thing that will change. So it'll get brighter or dimmer depending on the size of the lens here. So when you go to get glasses, one thing your optometrist will often ask you is, would you like thinner glasses? And of course, everyone wants thinner glasses, right? So for a few extra dollars, you can get thinner glasses. Now, how is this possible? What could she do to make this possible? In other words, to have thinner glasses that still allow you to see. So I'm actually not going to answer this right now. I want you to think about this question, and then in class, I'll ask it again, and I want to hear your response. Okay? All right, so that ends the lesson for today.